Okay, thank you for hanging with us. We shuffled the order due to technical issues. So I'm going to present this work that was led by a visiting scholar in my lab, Sarah Fabi, and she visited for 2 months and did this amazing job, and now she's busy giving job talks, and so that's why I'm giving the talk. It's built on the work of Xiaoxing Zhu, who was a PhD student with me, and she was a student in electrical and computer engineering when she did this work, making a computer vision recognition system for pain. Okay, so we're motivated by the issue that people often underestimate pain in people of color. And there's probably multiple reasons for this, but we were interested in exploring whether some part of this might be due to visibility differences in various facial muscle activations. There's also been really interesting talks both in this session and then earlier by Rachel Jack and Fernando Perez-Gay-Haraz, looking at other aspects in making more realistic stimuli. But we wanted to just look and see what we could see about visibility differences in various facial muscle activations. So we decided to test this using a computer vision model trained to recognize facial action units relevant for pain. Our work has multiple long-term goals. So one is understanding the basis of discrepancies in pain recognition for people of color. Another is to improve automated computer vision systems to remove these biases, both for pain recognition systems, but in general for facial recognition systems. And a long-term goal is to use this understanding to help people overcome perceptual differences in pain recognition when they look at people of different races and different skin colors. We use the FaceGen software, and is it working? It doesn't work on this machine. Well, these were videos that show the FaceGen software can morph and create faces of different skin colors and different morphologies, and also different facial expressions. For instance, it makes a European face, or makes a variety of European faces, African faces, and we are restricting our current analysis to studying they're European, the quotes mean because they're artificially generated, but European faces, African faces. We can also just have it make a random face, and then we will look at changing the skin color. So this is a random face, light skin, and this is the same random face where we change the skin coloring to be more dark. Okay, FaceGen generates facial expressions using the facial action coding system, and we considered 9 pain-related action units. Some of them are shown on this slide. The ones shown on this slide are related to the PSPI measurement, which is a measure created by Crichton and Solomon to be an estimate of pain. And we can look in more detail. So these are facial action units relevant to pain from the upper face and relevant to pain from the lower face. We use a computer vision model, the extended multitask learning model developed by Xiaoxing, and it's a 3-stage model. The first stage is based on, First stage is based on VGG face, and then trained to recognize facial action units, the 9 that we study relevant to pain, as well as this PSPI measure. After that, the statistics across the frames are combined to get a measure of pain, overall behavioral pain for the whole video. But for this work, we're looking at pain in images. So we just are concentrating on stage 1 of this model. Again, it's based on VGG face. And then after taking VGG face and then training the whole model on the McMaster UMBC pain data set to learn the AU and PSPI outputs. Here's just an example of PSPI as coded by a human in the blue, and then the output of the model in red on the McMaster pain data set on a test sample that it wasn't trained on. Okay. Okay, so we're going to basically give faces from the FaceGen model to our modified VGG face, And in particular, note that we're not going to train the model on these artificial faces. We're just going to test the model that was trained on the McMaster, UMBC McMaster pain data set. But we're going to be looking at the differences to the artificial African faces, the artificial European faces, and the artificial faces that are the same, but just changing the skin color. Okay, so what do we see when we do this? Overall, we do not see a difference in overall AU activation for dark versus light or for African versus European faces. But within action units, we see very strong differences. So AU6, this cheek razor, we see a significantly larger values for darker skin. And AU10 also, that's this. And then larger values for lighter skin or for AU43, that's just eye closing, AU25 lips parting, and AU26 jaw drop. This is when we take random faces, dark skin color versus light skin color. If we look instead and look at facial morphology differences and look at African versus European, these ones up here that do not have the blue boxes, these were also larger for dark faces and these were larger for light faces. So this is a consistent difference. Our African faces were all dark and our European faces were all light. But the blue boxes actually show differences now that differ a little bit due to the facial morphology. So facial morphology is involved in explaining these differences for African versus European faces. So we decided to look in more detail at a couple of these action units. So the first one we look at is AU25. This is lips parting. The model was given the full faces, but we just show the lips here in order for you to concentrate on this very subtle difference. You see, basically, you see more and more teeth as you go through here. The computer vision model is able to track increasing activation of the AU25. So this x-axis refers to activation put into FaceGen. So there's a FaceGen model. We tell it make 0% activation of AU25 versus make 100%, and then we stick it in the computer model and say, computer model, what do you say? And it does this output. So it's highly correlated. And it also is highly correlated for the European faces. But you'll notice that the axis is very different on these plots. So here are the plots as I showed them. Here are the plots if we make the axis the same. And you'll see there's a strong bias differing between the African faces and the European faces. And in fact, if we take the African face and we just lighten the skin color to be similar to the European skin color, we can explain this we can basically go from the output of the African face here over to the European. So this difference in AU25 is largely explained by skin color differences, which we can zoom in here. So here we have the African, an example of African, lightened, same African, European, and darkened European. Again, we did this though for many different random samples. But here you see, so if we compare the two red boxes here, you see that the lighter skin gives a higher AU25 activation. So these are same expression, just skin color changes. And this is the same expression in the European model. Again, much bigger AU25 activation for the lighter skin. If we compare the same colored boxes, now we're looking at the morphology changes. So this is the African face. This is the European face. You'll see there's not that much difference for AU25 for the facial features. We also looked at AU7 for a different example. So this, again, we see strong correlations with our computer vision model to varying the activation level of AU7, both in African and European faces. Again, we have this offset bias. And I note that in our talk, we're emphasizing the ones where the European faces had stronger activation, but there were other AUs that had stronger activation for the Africans. So I don't want you to come away with the idea that the model does better on European faces. We just picked these ones to explore. And so here you see this difference. And in this case, so if we change the skin color, we do not fully explain this differences between the AU7 activation. So here's the African face. And then as we lighten it to get to the European color, we only get up to around 17%. And over here, the European face over here is up at over 30%. So zooming in again, here's African face at -7. the lightened African face at 15, the European face at 33, and the darkened European at 17. Again, the lighter skin color gave a higher AU7 activation, but here we're comparing this to this and this one to this one. We also see that the European features give higher AU7 activation. And so what Sarah did next was she, to prove that the facial morphology was affecting AU7 model activation, she varied things systematically to actually try to explain this difference. So remember, the European face was up here around 35%. The African face was down here at -7%. Just using color alone, we got to the 15. So the color explained a lot. Overall facial shape then explained a little bit more, and then she could change eyes, forehead, brow, nose, cheeks, temples. And then these changes on mouth actually made it worse. So again, we're talking about this A activation unit around the eyes. And so these things were these are what made a difference in the European versus African. Interestingly, we noticed that while AU7 was more strongly activated in European faces, the AU6 was more strongly activated in dark and African faces. And so we decided to see that as she did these manipulations, she also then went back and looked at how AU6 varied. And you'll see that the model is basically trading off AU6 and AU7. And so that's interesting. They're both resulting in constriction of the eyes, but a carefully trained human observer should be able to tell, although the guidebook does have a lot of description on how to carefully tell the difference between AU6 and AU7, but it seems like the computer vision model here, and this is something we have to look more into, but is more able to recognize AU7 in the lighter faces and more able to recognize AU6 in the darker faces, and also with the more African shaped faces. Okay, so summary, limitations, and next step. Our computer vision model is affected by skin color and facial morphology. While the model was trained on mostly light faces from people of mostly European descent, some action units are more strongly recognized in our darker and African artificial faces. So it's not simply, like many biases in AI systems, you train it on white people and it works therefore on white people. Here, this model is largely trained on white people, but it recognizes some action units more strongly in Black or African faces and others more strongly in white and European faces. And we believe that is due to the visual differences. If you think about what the deep learning is doing, it's basically, it's applying little feature filters, and some of those are going to be more strongly activated depending on contrast differences in the face. As a caveat, we are relying on the face gen accurately creating AU activations and appropriate skin color and racial morphology changes. So for next steps, we're also relying on them being realistic enough. So for next steps, we're going to have trained observers confirm these AU face gen activations. We're also going to have regular humans make global pain judgments on these faces, and we're going to computer vision to do those pain judgments as well. And we're going to see if we can try to remove these biases in the computer vision model. And then, of course, our long-term goal is that can we actually then train people to remove these biases by emphasizing, hey, you can't see this activation unit as well in people with darker faces or people with lighter faces, etc. Okay, and so I have hit next slide on my thing and it has not advanced. My last slide is my acknowledgements, so I'm just waiting for it to come up. Okay, thank you. So again, this work was led by Sarah Fabi, building on the computer vision work of Xiaoxing Zhu. I have a large group of recently graduated and current undergraduate students working on various aspects of completing this. Mingzi Simpson and Lihan and Ritik and Miguel and Jin are all working on training new models with more realistic and more diverse stimuli. Will is working on the psychophysics to get human judgments. We have a variety of graduate students who are experts in psychophysics experiments, computer vision, deep learning, also psychophysics. This is also an expert in emotion perception. And then Philo gave us useful comments on our paper. And funding acknowledgements to UC San Diego Social Sciences for a Racial Justice Award, UC San Diego Sanford Institute for Empathy and Compassion for a Compassionate Empathy and Technology Award, University of Tübingen for a Travel Award for Sarah, and NVIDIA for providing the GPU that we run our models on. Thank you.